quantum mechanics. This is the world, as we just heard, is responsible for lots of technologies. Our understanding of how stars produce atoms, the different elements that constitute the world, but it's also the theory that explains how the transistor works in your smartphone, how the laser works. A lot of technologies and a lot of things we use in daily life, we understand because of quantum mechanics. But that quantum mechanics, which is so efficient and precise in explaining the world to us, is also a very strange theory. It works wonderfully, but it's weird, it is strange. And I want to emphasize that because we are now witnessing a second revolution of quantum physics, where we are not looking at the applications of atoms, we're not looking at the applications of materials, we're looking at applications of the weirdness, we're looking at applications of the strange character of quantum physics. So in the second part of the talk, I will talk from weird to wired. And what I'm going to cable together, what I'm going to wire together, is quantum behavior in building what we call a quantum computer. I could choose different topics. There are many new technologies we are dreaming about that will use the crazy quantum mechanics, but I've chosen to talk only about the quantum computer today. I'll tell you how it works, I'll tell you what the computer can do for us, and in the end I'll tell you how we try to build the quantum computer. The future machine that can solve very complicated problems. But let me take you back first to the early days of quantum mechanics. In fact, I want to take you back before quantum mechanics. I think 30,000 years ago, humans were sitting in front of the fireplace and they made an observation that when your fireplace is getting colder in the evening, then you will see the yellow color of the fire turn gradually red, until finally, of course, there's no fire anymore. And this cooling down, combined with the colors that are changing, is a phenomenon that physicists are actually obliged to explain. This is a physics question. Why does that happen? And it was observed in the late 19th century that we didn't have an explanation of that phenomenon. We had a theory for what was light. So what you see here is how all the colors are split, like in the rainbow or by a prism in the colors of the rainbow. And each of these colors are described by what we call waves. So Maxwell in the last century, the previous century, made a theory which explains light. Light is an electric phenomenon. It's actually electric and magnetic fields who are oscillating in space and time. So you imagine that you have electric fields going up and down, and now I'm just doing some wavy motion. I'm a theoretical physicist, so I don't need any experiment. I use my body if I want to think about things. So what you could imagine is electric fields who are moving up and down. That is, they are strong, weak, and at the same time they propagate through space. And that's Maxwell's theory for what is light. And the colors of light are actually associated to how fast they oscillate and how long is this modulation. So if I have a wave which is doing like that, that's a fairly long wave, but if I have this bending in the middle, I get shorter waves, and this corresponds to the shift from the red colors, which are the long waves, to the blue colors, which are shorter waves. Red waves also correspond to the slow frequency, and if you go to the higher frequencies, you get the shorter wavelengths of light. But that doesn't explain why the lower temperature gives you red colors, and the higher temperatures give you more the yellow and the white colors of the spectrum. And the answer to that question is actually the birth of quantum theory. So Max Planck, German scientist, year 1900, published an article in which he proposed that it's not only the electric fields going up and down, the strength by which it goes up and down is quantized. You cannot just have it go up and down by any amount. You can have a certain amount, or 2 times that, or 3 times that, or 4 times that. So that's what we call a quantum. When you go to the supermarket, you cannot buy any amount of wine. You can buy 1 bottle of wine or 2 bottles of wine. And you can get a quantum discount if you buy a lot of wine in your supermarket. But you cannot buy half a bottle of wine or a third of a bottle of wine. And the same thing is true for light. So the energy in light comes in quanta, which is really just a package of energy or a certain amount of energy. And now the story is that that package of energy has an energy which is proportional to the frequency of the light. So that means that these packages of energy, they have smaller energy for the red light and higher energy for the blue part of the spectrum. So what happens in your fire when it cools down is that there's less energy available. And when there's less energy, you get only the packets of energy with the low energy, and that's the red light. So of course there was also a formula, but I don't want to show you too many formulas or equations in this talk, but Max Planck, he actually made a formula that fitted perfectly with the distribution of colors in any light source that has a temperature. And you can show when the temperature goes up, the colors shift towards the yellow and white colors. So that's the name of quantum theory that comes from this point. There was another optical phenomenon, light phenomenon, that was not understood very well. And that's if you look at the spectrum, for example, of the light from the sun. So what I show you here is all the colors from the sun split out in different frequencies or different colors. And what you see from red, orange, yellow, green, and blue in the bottom is all the colors in the light from the sun. You also notice that and these dark stripes is not an error in my talk. These dark stripes correspond to missing light when you look at the light from the sun. So why is there light missing? Well, you could do an experiment in the lab, and that's what they did back in the 19th century. If you send light through a gas of atoms, you will notice that some colors actually go missing. And it's very characteristic, very well-defined colors that go missing. You can see these stripes are very narrow. They correspond to precisely that sort of red, precisely that sort of yellow, who gets lost. I have a white arrow that points to an orange line. That orange line is the same color as you see in the lamps on the highways when you go in your car in the evening. And what we know is, because we make them, these lamps contain a gas of sodium. So when you see exactly that color in the light from the sun, we know that there's sodium in the atmosphere of the sun. This is in fact a fantastic fingerprint. There's 100,000 such lines in the solar spectrum, and if you go to the lab, we can find every one of them. So that means we know exactly which atoms are in the sun. My astronomy friends, they do this for every single star you see in the sky. So every star that exists, when you go out tonight, you will see the stars. You can be sure that an astronomer has taken the colors from that star, and he can tell you exactly, or she can tell you exactly which atoms that star is made of. And that's part of the great story of astronomy. They can tell you how the universe developed, because they know exactly for each star which atoms are there, which atoms are being burned into other atoms. So it's a great evolution story of the universe. But that's not what I want to tell you about. But I want to tell you one thing, that is that several of the atoms we know today were actually discovered in the sun and in the stars before we found them here on Earth. And the famous one is named after the sun. So you know the sun is called Helios in Greek, and helium, the gas helium, which is in the balloons you can see outside, was actually not spotted on Earth first. It was spotted in the spectrum of the sun, and only 10 years later was helium discovered for the first time on Earth. So it's a very exciting story. We have these stripes coming from the different species of atoms. But nobody told us why. Why is it that sodium can only absorb or emit orange light? Why is it the neon light is red and precisely that color of red? And there was absolutely no explanation for that phenomenon. So that takes another physicist who also makes use of this quantum. And that physicist was a Danish physicist, Niels Bohr. So he's looking here at the spectrum coming from hydrogen atoms. Hydrogen atoms emit light of very distinguished colors. So you can see the prism again, but instead of having the full rainbow colors, there are only fused lights present. And Niels Bohr, he wanted to explain that. And part of the explanation is this planetary model where he says the hydrogen atom is an atomic nucleus, and then there's an electron who's moving around like the planets around the sun. And this is the model that you probably all learned in school. What is an atom? That's electrons moving around the atomic nucleus. This does not explain why you have only certain frequencies, because if you take the electron a little further out, it will go a little more slowly around the nucleus. Even further out, it will go even more slowly. So it seems that this electron could move at any frequency around the nucleus. So Bohr's model of the atom is actually not only that the electron is going around the nucleus, but it's a postulate, and that's a very strange way to make physics. Bohr, he postulated that the electron is not allowed to be at any distance. It can only be at distance number 1, distance number 2, distance number 3. It's almost like if there are train tracks around the atomic nucleus, and the electron has to be on these tracks. So that's a postulate by Bohr. There's nobody who has ever done an experiment who says it's right. But by construction, that model will explain that there will only be particular frequencies of the light. So this is what Bohr was doing in 1913. He said these particular orbits are the ones that exist. He also had a trick up his sleeve, so because he was smart, he could actually give a plausible argument why these should be the allowed orbits. And that plausible argument gave an equation, a formula. And that formula fitted exactly with all the measured frequency of hydrogen with 6-digit precision. There's never in the natural sciences been a measurement that fitted theory to experiment with 6-digit precision. So even though people were skeptical because it was not a real theory, but just Bohr postulating something, it was still amazing that he would get all these numbers right. So Bohr's theory was a big success, And it would have been a fun story, but not nearly as fun as the one I will tell you, if it had been right. But Bohr's theory is actually wrong, and it turned out that it breaks down. You can use it wonderfully for one single atom, but in physics we're a little more ambitious than that. If we want a theory should work, of course, for all atoms. I don't want to make a new theory for helium atom and a new theory for the neon atom. I want general rules that I can use everywhere. And the rules that Bohr applied do not work for any other atom but hydrogen. So it goes wrong, and eventually you had to abandon Bohr's theory. And then you realize that you don't have any theory at all anymore. So what can you do? And a French scientist, he had a proposal. He said, maybe we should not throw it out completely, but maybe we should not literally think that it's a particle moving around. Maybe we should just think about some other principle. And the French physicist, Louis de Broglie, he proposed that it should be a wave going around. Now what does that mean? Well, a wave is something going up and down. So if you imagine that you have something going up and down around this round trip around the nucleus, then you could imagine that that going up and down motion bites its own tail. And what de Broglie proposed was that the allowed orbits in Bohr's theory are exactly the one where this wave bites its own tail. So it can make one excursion in and out and come back again, or it could make two excursions in and out and come back again. And these different orbits should then be the Bohr orbits. Of course, nobody really knows what it is that is waving like that, but the very idea that by putting in such a principle that you should have a whole number of these oscillations also forces the orbits to be numbered by how many of these oscillations are there. Number 1, number 2, number 3. So this is one ingredient. I personally think that de Broglie may have had another source of inspiration, because waves can do something very naturally if you think about it. Waves very often give frequencies, and very distinct frequencies, for free. Yesterday there was a great concert with Pat Metheny, and if you take a guitar and you pluck the string, it doesn't play at any frequencies. It actually plays a tone. And why does it play that particular tone? That's because the string has to move up and down. And the wavelength of that string motion is exactly given by the length of the string. So, you know, some small instruments play high tones, long instruments play the deep tones, and it's really the wavy motion that forces the frequency to come out. You don't have a choice, if you're a guitar string, to go a little bit faster up and down. At least that's what the way music works. You play the string and it plays a certain tone for you. So waves naturally come and give frequencies. If you blow into an empty bottle, you get a certain sound because the wave motion of the air inside that bottle likes that frequency. Drink a little bit, the frequency goes down and it gets deeper. So wave physics, wave mathematics likes to give you particular frequencies. And that's of course exactly what we want from our atoms, because all atoms send light out with very special frequencies. So I think that de Broglie has had a combination of intuition for that, and then some idea that this could maybe also explain how it exactly fits. And note also, when I say the wave should fit, like in the pictures I show you here, it's also what the guitar string does. It exactly fits to be at rest at the end of the string where it's attached to the guitar while the string is moving up and down. It's not real theory, it's just an idea that waves could have something to do with it. But of course, then you go and tell a physicist, could you please find out what is that wave? What is the wave we're talking about? And it just takes a bit of mathematics and a little bit of knowledge. How do we actually describe waves to move on and try to get equations? And this is Erwin Schrödinger. And Schrödinger, he decided to try to find a mathematical theory for waves that would describe this wave phenomenon. Now, as I told you, physicists know how to deal with waves. I show you a picture of a water surface. The way waves propagate along a surface is of course something we can describe mathematically. The way that sound propagates in this room is also by waves, and that's also something we can describe mathematically. And don't be scared, but now I will actually show you the equation that Schrödinger wrote down late 1925, early 1926. This is Schrödinger's equation. I get happy every time I see it, but if you don't like it, think of it as abstract art. It really doesn't matter, because there's no exam after this talk. So you just notice that there's a piece of mathematics, and it's mathematics who describes the shape of this particular wave phenomenon, and it actually solves, if you know what it looks like now, what would it look like a little bit later, a little bit later, a little bit later, a little bit later. And the equation is exactly doing that. It just tells what is the change per time of the value. And the reason it's a difficult equation is because it's not just one particle moving. It's the whole arm or the whole wave who is moving. So I have to tell what happens with this piece of my arm, this piece, this piece, this piece, and this piece. So it does get a little bit complicated. It gets that complicated. But that equation is not any harder than the equation for a guitar string, or for the skin of a drum, or for the air in this room, who is also solving wave equations. So no physicist would be terrified by this equation. Schrödinger solved it. And here are the solutions. And of course, what do I mean by that? I mean that you find solutions to the problem, and then with colors you show where are the numbers large and small for this object who is waving. Of course, if it was a string, it would be how many centimeters is my arm moving up and down. But in this case, it's just the solution to the equation which is shown. You recognize it looks like if you drop a stone in a pond, then there will be waves of water propagating away in a ring pattern. But there are also more complicated patterns, and these are all different solutions to the same equation. They all oscillate in time, and they oscillate with exactly the same frequencies as we see as the light frequencies of the hydrogen atom. So it gives exactly the same result as Bohr's theory, but now no postulates, just one equation we have to solve. And I cannot refrain from showing you a picture of a guitar. I already mentioned the string of the guitar. In fact, what you hear is not the string. The string motion is transferred to the air inside the guitar, and the whole body of the guitar is moving. And if you borrow a police radar, the ones they use to measure the speed of your car, and you look at a guitar with such a radar, then you can see how the surface of the guitar is moving. And what you see on the left is the guitar playing a deep tone, and the two sides are moving in and out towards you with a deep tone. And what you see on the right is 6 areas who are moving out of phase, in and out and in and out. That's when the guitar plays a higher tone. And if you look at the solutions by Schrödinger, you can see they match actually. There's 2 areas in the Schrödinger solution for quantum mechanics that look like the guitar motion. And there's also one with 6 areas moving in and out in agreement with what you find from the guitar. So the connection between the wave solutions for music instruments and the wave solution for this Schrödinger equation is actually quite perfect. But what does the wave function mean? There's a difference between solving the wave equation for water, where I want to know the height of the surface of water, I do some mathematics, I get a solution out, but 2 means 2 centimeters. And here, where we started with the mathematics, but we don't know what we describe. The wave function is not a wave of anything. It's just a wave of mathematics. And when you look at these pictures I showed you, nobody at the time knew what they actually meant. Well, I say nobody, but in fact, it's not John Travolta, but Olivia Newton-John standing next to him from the Grease poster had a grandfather, and Olivia Newton-John's grandfather was called Max Born, and he was a German physicist, and Max Born gave an interpretation of the quantum mechanical wave function. He made the observation that if you take physical situations where particles bump into each other, you can find out how do they scatter out in all kinds of different directions after such collision processes. And studying that and comparing with the wave function, he found that the distribution of the scattered particles, how many go out in 10 degrees, how many go out in 20 degrees, 30 degrees, match exactly the shape of the wave function. So what we call the Born interpretation of the wave function is this idea that the wave function describes where the particles go in some way. So the quantum mechanics, which is exactly the same as solving Schrödinger's equation, is a theory that predicts energies wonderfully well. Today we can do some calculations where we have 12-digit precision. We can calculate the energy and we tell you what it is, and then after that we go and measure it, and it matches on every digit for the first 12 digits. But at the same time, we also tell you where the particles are, but not precisely. If you do 1 million particles, I can tell you how many are in different directions. If you have only